So guys, today we're going to discuss the Gauss law and electric potential. So the Coulomb's law can be expressed in a form known as the Gauss law. The determination of the electric field using the Gauss law actually appears to be easier for us, but the number of problems we can solve using the Gauss law can just be limited, because the charge distribution must have a special symmetry property. So let's start by defining the electric flux this way, as electric flux is equal to AA cos theta, where E is the electric field, and then A is the area, and then we have cos theta, which is the angle represented. So let's simply go ahead and solve some exercises on this using the electric flux. So I'll go ahead and wipe this. So the question says, at each point on the rectangular surface shown below, the electric field has a magnitude of 350 newtons per coulomb and makes an angle of 50 degrees with N. Then calculate the electric flux for this surface. So we are going to actually have our solution here. So the first step to take is to use our formula for electric flux, which is EA cos theta. Alright, so the flux here is the electric field times the area, then times cos theta. So what's the electric field from the question? 350 newtons per coulomb. So we're going to multiply 350 newtons per coulomb times the area. Now notice that we have 20 cm and we have 15 cm. And what our area to be in meters? So we're going to simply convert the 20 cm to the standard unit in meters, and 20 cm is 20 over 100 meters, which is 0.2 meters, and then 15 cm in meters is 15 over 100, which is 0.15 meters. So in order to get the area, I'll have 0.2 meters times 0.15 meters, which is 3 times 10 raised to the power of minus 2, or simply 0.03. So I'll go ahead and wipe off this part. Now I know that the area is now 3 times 10 to the power of minus 2. And then I'll multiply this by cos theta, which is in this case cos 50. So when we check this with our calculator, we should have 6.74 Newton meters per coulomb. So that is it. I'll go ahead and wipe this. So let's consider the statement of the Gauss law. Now the Gauss law states that the surface integral of the normal component of an electric field through any closed surface containing a total charge Q is given as Q over E naught. as the charge over epsilon naught. So simply we are going to have that the flux is equal to Q, which is the charge, over epsilon naught. Right, so having known this, for a charged conducting sheet of area A, the total flux of such a sheet will be EA. So in such a case, from the Gauss law, we're supposed to have EA is equal to Q over E naught. And then thus we'll have E, electric field, as Q over A times E naught, where A is the area, E is the electric field, and Q is the charge. Alright, I'll go ahead and write this so we can proceed further. So we can also find E from the linear charge density, from the area charge density, and from the volume charge density. So we can use the linear charge density, the volume charge density, and the area charge density in calculations involving the electric field with the principles of the Gauss law. So I'll probably go ahead and take you through this, and then we'll see how we can apply the linear charge density, surface charge density, and volume charge density. Alright, now lambda is used to represent the linear charge density, and then the linear charge density is always given by Q over L. That's the charge over the length. Alright, so the surface charge density or the area charge density is given by Q over A, where Q is the charge and A is the area or the surface area of the solid. Alright, so lastly we have the volume charge density denoted by rho, which is given by Q over V, where Q is the charge and then V is the volume. So for a cylinder of radius R and length L, we have the area 2 pi RL. Now if the area is this, we can actually apply it to this formula as EA is equal to Q over E naught. Now what do? We can replace the area by this. So we now say 2 pi RL E is equal to Q over E naught. Now if I want to place E as the subject of this formula, I can simply have something like this over 2 pi R L E naught. Alright, I'll go ahead and write this for space. So since I have my E to be Q over 2 pi RL E naught. I can actually replace this with my linear charge density. And how do I do that? I'll have to recall that my linear charge density is Q over L. So if I have to replace Q by my linear charge density lambda, I'll simply do this. A, which is the electric field, is equal to lambda over 2 pi r L E naught to pi r L E naught, then times L. And since Q over L is lambda, it means that Q is lambda times L. So if I multiply this, I'll have to cancel off L, and then ultimately I'll have E to be lambda over 2 pi r E naught. So this gives us the electric field using the linear charge density. Alright, I'll assume this is clear to you, and then we'll move further to see that of area charge density. So supposing for the same cylinder, remember the area is 2 pi r L. So supposing we want to use the surface charge density, all we have to do is always remember that EA is the charge over epsilon naught, and then area is this, so I can always replace this by 2 pi RL, then times E, and this is Q over E naught. Then if we should have this 2 pi RLE is equal to Q, which is the charge over E naught. Let's say we want to make E the subject of the formula. This becomes Q over 2 pi RL E naught. Alright, so let's recall that our surface charge density is given by the charge over the area. Now this actually means that the surface charge density is the charge over the area of the cylinder in this case, which is 2 pi RL. Now this makes it simpler for us. Now since the charge is this, it means that Q is also the surface charge density times this surface area, which is 2 pi RL. So we can always replace Q by this in this equation. So if we have this, we're definitely going to have E to be sigma, which is the surface charge density, times 2 pi RL over 2 pi RL E naught. Now, see how simple it can be. We can cancel off this, and then E now becomes sigma over E naught, or the surface charge density over E naught. Alright guys, so I'll go ahead and wipe this. So we'll move up a bit to the next level, which is volume charge density. So now for a solid sphere charged with a constant volume density, and remember the volume density is rho, and it's equal to the charge over the volume. Alright, so for a solid sphere charged with a constant volume density rho, we will always have AE or EA to be equal to Q over E naught. So what's the surface area of the sphere in this case? Now the surface area of this sphere will be 4 pi r squared. So this gives us that 4 pi r squared E is equal to Q over E naught. Now, let's set aside this. Let's also remember that the volume of a sphere is equal to 4 over 3 pi r cube. So while the area is 4 pi r squared. So always take note of this. So let's get back to this. Now, if we have this and we want to make E the subject of this formula, we are simply going to have E to be Q over 4 pi r squared times E naught. Now, in this case, we want to replace RQ with the volume charge density. So we'll recall that the volume charge density rho is equal to Q over the volume, which is 4 over 3 pi r 4 over 3 pi r cubed. Now, if this is true for this, it means that Q is equal to rho times 4 over 3 pi r cubed. So for this, we can replace Q by this. So simply have E to be rho times 4 over 3 pi r cubed, and this is over 4 times pi times r squared times E naught. So this is 4 pi r squared E naught. Now notice I have 4 pi r squared here and I have 4 pi r cubed here. If I go ahead and make a division here, I should have just r remaining here, and then this is 1 over 3 here. So ultimately I'm going to have my E to be rho over E naught times 1 over 3 r. And remember, this is r cubed and this is r squared. So when you divide this, you should just have r. Now 4 here is 1. This is pi goes for pi, and then this is 1 over 3. So ultimately I have E to be the volume charge density rho over E naught in times 1 over 3 R. So let's go ahead and wipe this. Alright, so since we have E to be this, let's also recall that rho is Q over the volume. So we can also get back to something familiar. So let's see this. Since rho is Q over V and this is rho here, and the volume, as you can remember, is 4 over 3 pi r cubed. So this is Q over 4 over 3 pi r cubed, right? Makes more sense this way. So I can replace rho by this, and then in this equation I should have something like Q over 4 over 3 pi r cubed, and this is over E naught, and then this is times 1 over 3 r. Now if I should break this down, I'll have E is, now this is Q divided by 4 over 3 pi r cubed. Now the 3 has to go up, and then I'll have 3Q over 4 times this, 4 times pi r cubed times E naught, and then all these times 1 over 3 r. Alright, at this point I can cancel off my 3 here with 3, and then if I multiply these out, so let me make a space here. E to be equal to, now Q times R over 4 pi, let's see, E naught R cubed. Now this makes it simpler for us because we can actually cancel R for this, and then you'll have R squared here. So ultimately we're going to have Q over 4 pi E naught R squared. This looks familiar. Yes. Yeah. So that will be the end for this class, and then we'll move ahead to solve other examples in our next class. If you enjoyed this video, please give it a thumbs up. Also share and comment on the comment section below.